Yes, exactly. All right, here we go. This is a continuation of Pre-Calculus 24.4. We're talking about the quadratic formula, and an important part of the quadratic formula is something called the discriminant. Okay? Everyone paying attention now? So the formula itself gives you the numerical values for the roots of an equation, of a quadratic equation. And as we talked a little bit about yesterday, the roots or the solutions don't tell you much about the graph. They don't necessarily tell you much about the context of the question. They are the values of the roots. Now, the nature of the roots and what the graphs look like and how many roots can be dictated by something called the discriminant. So if you think about the root of discriminant, like discriminate, you guys listening? Yeah. Discriminate means to like accept some, reject others, okay? Or to really determine sort of what is, what's true about this. So the discriminant is the portion of the quadratic formula right here. It's this part. It's the b squared minus 4ac. That's called the discriminant. And it's going to tell us a lot about the nature of the roots, the graph, and how many roots there are. So let's talk a little bit about that. Now, first of all, we need to know what A, what B, and what C are for the quadratic equation. And so we do need to know, we kind of need the coefficients here, these are all numbers, from the standard form. So if it's not in standard form, you don't have A, B, and C. Okay, boys, can you guys just stop?
Yeah. I'm just trying to memorize the...
Okay, all right. You're distracting me over there. Okay, you're dancing. Okay, thank you. So you do need to know what A, B, and C are in order to use this formula. And obviously A, B, and C are in the discriminant. So you've already started to jot down this table already. So the discriminant here, if the discriminant, b squared minus 4ac, is a positive perfect square number. So the actual value underneath the root sign here is a positive number, and it's actually a perfect square. So an example, obviously, would be something like, the discriminant is 9, okay? So b squared minus 4ac ends up to be 9, the value 9. So the number of real roots that we have when the discriminant is a positive perfect square is going to be, any guesses?
2.
2 real roots. Okay? 2 real roots. Now think back to this, because we had, last lesson, we had a number plus a number over 2a, and then a number minus a number over 2a, 2 different roots. Okay? So the type of roots, okay? They are rational roots. That's what I'm looking for, rational. So that means that there's no root sign left in your answer, because the root sign just goes away if it's a perfect square, right? So like if we have root 9 is 3 for our example. See, 9, root 9 is 3. There's no radical left, so they are rational roots. Now they could be fractions, but there's no radicals. So maybe I'll just put that. So no square root sign. Let's say no square root sign in the answer. Okay, so they're rational. Whoa, and rational just disappeared.
Like 10, like root 10, that would be a radical?
So yeah, so that's going to be the next type, positive non-perfect square. So we'll get to that in a second. Okay, let's finish up the graph here. So we're going to have a graph that is going to have 2 real roots, something like this. And in this example, this is going to be a -3, and this will be, wow. Anyway, it could be like this. So -3, positive 3. It might not be exactly what the square root of this radical is, because there's other things. There's the b, there's the 2a, all that. Okay, but that's an example. Okay, it'll be some whole number or integer, and fraction or a fraction. It's not going to have a radical in it. Okay, the next option would be a positive non-perfect square. So an example of that might be, like you said, 10. Okay? 10. So we're going to have still 2 roots here, but the types of roots are going to be irrational. Okay, so root 10 doesn't really simplify to anything. it's going to be root 10. And we're not going to go to a decimal. We're going to try and keep the radicals in the answer because radicals are exact answers, decimals are approximations. Okay? So you do have a square root sign. Square root in the solution. Square root in the solution there. All right, so the graph might look, I mean, you'll still have two roots, right? So it could just, be something like this. But these roots here are not going to be integers. They're going to be something, 1 plus root 2 over 5 or something like that. They're going to be irrational roots. So still two roots, but non-whole numbers, non-integers. Okay, so non-integer roots. Sorry?
How do you know that it's over there?
You don't. That's just an example. These are just example. It's an example graph. Okay? So still have two roots. It'll still cross twice. Okay, 0. So what happens if the D is 0?
1.
One what? One root? Okay, so think about that. We go back up here. If this whole thing is 0, then I just have this plus or minus 0 over 2a. So it's just really negative b over 2a.
Yeah.
That's it. Yeah. No, you're right. So how many real roots? There's going to be one real root. Now, in some ways, you might see this written. Guys, listen up. You might see this written. It's a little bit of, I don't know. It's kind of picky. I don't know if it doesn't really make a lot of sense, but you might see that there are two identical real roots. You might see that. I've seen that before. And why is that? Well, it's because it's negative b plus 0 over 2a and negative b minus 0 over 2a. Technically, you get two roots here, but plus 0, minus 0, they're the same. So I'm just going to say 1, because in reality, there's just kind of one root. Now, the graph, I'm going to flip right over to the graph here. So an example would be where the parabola just touches the graph at one point, like the vertex is on the x-axis, or something like this. Okay? So it just touches at one point. So this is also going to be rational as well, because we have a root 0 is just 0. So no root signs left. Okay? All right, so what happens if D is negative? Because this is the only other option now. So D is like negative 5 or something. Okay, so if we have to find a solution that involves a square root of a negative number, that is not a real value. So you try on your calculator the square root of negative something, and it'll say error, okay? Or it'll say something else, whatever your calculator says. But it won't be able to give you an answer. Now, technically, there's no real answer. My calculator is firing up. Technically, there's no real roots. There would be, technically, and you'll find this out later, but there technically would be, see, look at, this says error, look at non-real answer. This is what my calculator says. So technically, there is a non-real answer. There's an answer. It's just not a real number. It's a complex number, or a number that has, get this, an imaginary part. Now, think about this. We have, think about this. On a sheet of paper, you have two dimensions, right? X, Y. You don't technically have a third dimension that we can draw on the paper. You have to make it look like there's a third dimension, like draw some 3D shape. In real life, okay, you and me, we have three dimensions. We have length, width, and height, or length, depth, and height, or whatever you want to call it. So there's three dimensions. We operate in more dimensions than this, because there's time, right? There's the spiritual dimension, right? There's our mind, whatever that dimension is, right? That's beyond our physical brain. A lot of people want to deny all that kind of stuff. But there are other dimensions as well that we can't express literally in 3D space. It's beyond that. So a number that is not real would be able to be expressed, but you'd have to add a dimension to the number system that we see. So if we have a number line like this, number line positive all the way to infinity, and then negative numbers all the way to negative infinity, Then the complex numbers would be, a dot that's not on that line, but a dot that's off the line. It would be out here somewhere, not on the line. See, that's like the real numbers, and then complex numbers would be in some other space not on the line. Yeah, go ahead.
So, if there's like imaginary numbers, like what are they used for? I can't imagine that they'd be used for like real life situations.
No, well, if they're, what would they be used for? Not a lot of real life situations. The thing about math is math is an attempt to grasp reality, but not necessarily concrete reality. There's a lot of abstract things. So, for example, and again, I don't want to talk too much about this, but where complex numbers came from is the solution to this quadratic equation. That's where the idea of a complex or the imaginary unit came from. So there's no real answer that satisfies this, because this would have to be equal to -1, right? So if you take the square root of this, the only answer that you might get would be x equals the square root of -1, which is a non-real answer. Guys, zip it. Okay, now I'm telling you to zip it. Okay, non-real answer. So this square root of -1 is actually given a special letter, and that's I, the square root of -1. So this is technically a solution to this equation, but it's not a real solution. So I'm going to expand on that just a little bit. So you're right, there's 0 real roots. There's 0 real roots. And notice I put number of real roots. So there's 0 real roots. The type of roots would be complex. So not rational, not irrational, not 0. Complex is what they call them. And again, I won't talk too much about that. But the graph, what you guys are concerned with, is this would be an example of a graph that does not touch the x-axis at all. So something like this. Touch the y-axis, no problem. Every parabola does eventually, whether it's way up here or way down here. But it won't touch the x-axis. So are there any roots? Yes, but they're imaginary. They're complex. So no real roots. So we would just say, for our context, that there's no roots. But technically, it's no real roots. Does that make sense? So another cool thing about math is that, you can use your imagination to solve math problems too. We're not going to work with imaginary units and complex numbers here very much in this course, for sure. I'll just mention it. Yeah.
When would we work with imaginary numbers?
In upper level math, yeah. At university, a lot. In high school, yeah. I think we talk about I in maybe pre-cal 30.
So do
I think they changed the curriculum, so I don't know. I have to go back and look. But we can talk a little bit about it. Yeah.
Do NASA scientists work with those types of numbers, because then wouldn't they be basing a guy's life on a manual?
All right.
God.
Any questions about the discriminant at all? No? Good? Okay. The discriminant. So if you're looking for a solution, so let's just say this. Is there an answer to a certain quadratic equation? Is there an answer? Well, what you would do is you would check the discriminant first, and then you would determine whether there's an answer. And it'll tell you whether there's 1, 0, 2 answers. So you literally do b squared minus 4ac. You calculate that first, and then you examine that. Is it a perfect square? Okay, good. I know that there are two different solutions. Is it non-perfect square? Good. I know there are 2 irrational solutions. Is it 0? There's 1 solution. Is it negative? I don't even bother. There's no real answer. So there's no solution. So that's something that you can find out for sure whether there's an answer before you go through all the trouble of trying to find one, if that makes sense. If you don't do that first, you'll use the quadratic formula, let's say, and then you'll find in your calculations that you'll have a negative number under here, and then you can't go any further. There's no real answer. All right, so here's your assignment. If you didn't write that down yesterday, I don't know if I got to that. I think I asked you to do number 3. You could do number 3 yesterday after the first part of the lesson.
Wait, what do you mean by choosing?
But here's the assignment. 1 to 5, so do 1 AC, 2 AC, 3 AC, 4 AC, 5 AC. Do 7, 8. And I want you to choose your own question from number 9 to 20. The reason why I do this sometimes is because there are word problems that have like different applications. They're different. Some of them are about science, about rocketry. Some of them are about art. Some of them are about colors. Yeah, you just pick one word problem. So look at the questions, see what you might be interested in, and do that question. Got it? Got it?
When you say AC, is that just AC?
This one was actually for the x-intercepts. I don't